Now let's take a look at the bilinear membrane element. And discuss its behavior. We implemented that element, we solved a cantilever problem. But when we look at the displacements with the one element solution, we got almost 20 times stiffer behavior. We just use more elements, 5 element solution, it's approximately 2 times stiff. Now we have to figure out why this element behave stiffer than we expect. So for this purpose, let's take a single element and apply moment from both sides. So I'm taking a single element and then we apply moment from both sides. So what do we expect as a deform shape? So with these two moments, we are just inducing a symmetrical bending mode, right? Like the Legend, think about the beam element obtained with the general interpolation functions. So with the symmetrical bending mode, there is no shear stiffness, or we can just say that in this case, shear strain should be zero. Or of course you can, if you go from the force side, we have constant moment on this element, shear force is equal to 0, hence there shouldn't be any shear deformation. So with this loading, the expected deform shape should be as follows. And since we said that there shouldn't be any shear deformation, these angles must be equal to, again, 90 degrees. So the deform shape of the element should look like this under constant moment. So what we see at these top and bottom edges is we see curves, right? So in order for this element that to undergo only bending deformation, no shear deformation, we have to have curves at the top and bottom edges. So that's the expected deform shape. And let's also say that the corner angles should not change. Because shear strains should be 0. Now, what will happen when we use the bilinear interpolation? So, with bilinear interpolation, let's put however here. Let me draw the same element. So we apply moment again. So with the bilinear interpolation, we are saying that the edges should remain linear, right? It's because we don't have any other information in our displacement interpolation. So this is what we are saying, the edge should remain linear. That's the way we are interpolating the deformed shape of this member. So with this case, the edge can only deform linearly. Now let's take a look at the corners now. So as you see, we see a huge angle change. When we apply a moment, the deformed shape causes an angle change, which tells us that these moments cause high shear strains. All right. So what happens is this element resists the moment with shear deformation rather than banding deformation. And because of this reason, the element behaves much stiffer under banding. Because of this linear interpolation, the element behaves much stiffer. And this is a known phenomena, actually. This phenomenon is known as as membrane or shear locking. How do we avoid locking? Let's take a look at it. The very direct answer is use finer mesh. Okay, or more elements. We saw the cantilever with 20 times stiffer, with 5 elements, 2 times stiffer. Maybe if I use 20 elements, I'll get a better result. 100 elements, a much better result, right? But this is not what we want to do. We want to solve this problem. We catched it and we want to solve it, and we know why it's happening. It's because of the linear interpolation. So what we need to do is to increase the degree of the interpolation functions. So that could be another option. Use higher order shape functions. What's the downside? So in order for me to define a quadratic shape function, for example, I need additional nodes, right? Because think about it this way, if I have 2 nodes, the only function that I can define by using these 2 nodes is a line. But if I add another node here, I can define a quadratic function by using these 3 nodes. So the higher order, if I want to use a higher order shape function, I can have, or I should have 8 node elements. So I should have the mid node elements, mid nodes also. So I should try 8 node membrane elements to solve this locking problem. What's the downside? So for I can use less elements, but for every element I have to define 8 nodes. That could be preferable, but in today's world, no one in the practical engineering world, people didn't prefer to use these 8 node elements. They want to use simpler elements. So what else can we do? We can have 4 node elements with additional higher order terms. But in the previous case, we said that it's not possible if you have 4 nodes. We will see how we can make it work. And this type of elements are called incompatible elements. So if you examine the literature, you will see that there are papers, there are elements that use the assumed strain field approach. So basically this approach is the strain field is obtained using a definition. You can use the nodal nodes and combine them, the nodal degrees of freedom, with certain rules. So you define it instead of calculating it. From displacement derivatives. So basically this approach does this. You know, if you have a constant moment, you should have 0 shear strain, right? And if you have a different moments, then you have a constant shear strain within the element. So by using this information, you can come up with certain assumed strain field within the element. And one final approach could be adding additional degrees of freedom to the nodes. So we have 2 degrees of freedoms at every node. So I can add a drilling degrees of freedom and do the formulation accordingly. So since I have more information at the nodes, I can define a higher order shape functions. Degrees of freedom allows higher order shape function definition. So next week we will be talking about the remedies to avoid shear locking, and the first thing that we will be talking about is the incompatible modes. And the second discussion will be on adding the drilling degrees of freedoms. So we will discuss these two cases in the upcoming classes. Let's very briefly discuss how we can calculate the stresses, at a finite element. What are the things that we should be paying attention to? So let's put a heading, let's say stress calculation. Now, we know that the stress is equal to constitutive relationship multiplied by the strains. And we said that strains can be calculated by multiplying the B with the displacement. So at the end of once we obtain the displacements with the following equation, we can calculate the stresses anywhere we want in the element. But this B matrix, remember that, involves the first derivatives of displacement. Right, this expression, especially for this membrane element. And also let's remember that our discrete solution approach minimizes the error of the approximate solution and forces equilibrium condition only at nodes, okay? So in between the nodes, how much error we get depends on the shape functions that you are using and of course the number of elements that you are using, okay? Now, let's assume the following displacement field between two nodes. So let's assume that we have the following displacement field between two nodes. Let's say that that's node I, that's node J, and my exact displacement field. Let's simplify it. Let's use a linear variation. Is like this. That's the exact displacement field. Now we said that we do some approximation, right? And in between or at the nodes we have very small error. So let's say that that's the error in displacement. And let's say that here again a small amount of error. And what we calculate as a displacement field is as follows. And when you look at the displacement, you see that the error is not significant. Okay, but when you take the derivative of the displacements, so let's do that. Let's take a look at the derivative of the displacements. So I have again I here and j here. So I'm looking at the slope of this line, right? So the exact strain field could be this much. But when you look at the displacement field, the approximate displacement field, and take the derivative of it, you will see that the small errors that you see here can be significantly magnified. So let's write down what we observed. Even though the error in displacements is small, the error in strains can be magnified significantly due to differentiation. Okay, so this is what we observe. So this tells us that if you really want to calculate the stress in a displacement based formulation, you have to reduce the error in the displacements. In other words, you have to use more elements, and you have to be very careful while using this stresses, because of this reason you may have the small errors, but the small errors can be magnified significantly. The other thing is, here I used linear interpolation in between, but let's say that the exact displacement field is not linear. It has a variation like that, and we are approximated that with a linear interpolation. So we do have errors not only at the nodes, but also at the interior points, which may also increase the error in the stresses. So what do we do? How do we calculate the stresses? So several studies show that the optimal point for computing stresses are Gauss points, are the points where we do the numerical integration. So if we take our element at the natural coordinate system, so that's psi, that's nu, and if you think about it, we are doing integration at these points. If we use 2-point integration, so this one is 1 over root 3, 1 over root 3. This one is minus 1 over root 3 and minus 1 over root 3, and so on. But of course, calculating the stresses at the Gauss points is not practical, because when you look at the mesh of a structure, you don't really know where the Gauss points are. So you really want to calculate the stresses at the nodes. So there are so what we can do, directly obtain stresses at nodes. That's one possibility, but of course depending on the element formulation and especially your element sensitivity to mesh distortion determines whether this is a good idea or not. How do we calculate the stresses at the nodes directly? We write stress is equal to E times B times U and evaluate B at -1, -1, 1 minus 1, 1 and 1, and -1 and 1. This will directly give you the stresses at 4 corners. That could be one option. That's what I did in the implementation of the membrane element. So the other option could be obtain stresses at Gauss points and then extrapolate them to nodes. So in certain elements, you will see that this will produces better results than directly obtaining the stresses at the nodes. But when we do material nonlinear analysis, for example, we question the nonlinearity of the element only at the Gauss points, because we know that we get stresses and strains at these points much more accurate than the other location. This is mainly related with the integration method that we use, and I will give you some references that shows that these are the better points to calculate the stresses.